Today in the workshop, we'll be working with basic logic gates. We'll see how these devices work, how to select them, and how to use them by themselves or with an Arduino. We'll even build a simple intruder alarm. It's the logical thing to do, so welcome to the workshop. Well, hello and welcome to the workshop, and today we are going to be working with basic logic chips. Now, you may be wondering, why on earth are we covering basic logic chips? After all, some of these chips are over half a century old. What possible reason in the age of microcontrollers and microcomputers could we have for working with basic logic chips? Well, there are a number of reasons, actually. The first reason may just be academic. You may just want to know more about the fundamental building blocks of logic, because these are the building blocks that create every digital device that we have. But there are reasons beyond the academic for learning about basic logic chips. You may indeed want to use them in a brand new design. Now, that isn't a crazy thought. If you go on to a big site like Mouser or DigiKey or another large electronic distributor, you will notice that they have lots and lots of basic logic chips of 7400 and 4000 series logic chips, and that these are stocked in great quantities, and that the majority of them are surface mount. So these aren't chips that are just being used to repair old Apple IIs. These are chips that are being used for brand new designs, and there's a lot of good reasons for doing that. If you have a very simple design, well, a microcontroller can be an overkill. The most obvious example is the very first sketch that we learn with the Arduino, the blink sketch. If you want to blink an LED, there are better ways and cheaper ways of doing it than using a microcontroller. Obviously, the cheapest way is just to buy a flashing LED. But you can also flash a regular LED with basic logic chips or with something like a 555 timer. And the circuit that you'll wind up with will not only be less expensive than the one based around the microcontroller, it won't require any programming. It'll be easier to repair down the road because you can just simply replace components without needing to program them. And in many ways, it'll be more reliable because you're not going to run into software glitches or microcontrollers locking up. Once they're built, they just work. And a third reason for learning about basic logic chips is to enhance our designs based around microcontrollers and microcomputers. Now, we've already done that here in the workshop. A few episodes back, we used shift registers to enhance the input and output capabilities of an Arduino, and you can use all sorts of logic chips to enhance and improve your microcontroller-based designs, and we're going to be doing that a little later on in today's episode. Now, basic logic chips is a huge subject, and to cover everything in one video or one article would be absolutely ridiculous and probably impossible. So what we're going to cover today are the fundamentals, the fundamental logic blocks that comprise everything that we have that is digital these days. We will cover all of that. We'll also cover logic families, specifically the 7400 TTL series of logic families, which is what we're going to be using. We'll of course do a couple of designs by wiring these chips up, and we will also bring an Arduino into the picture. We will show you how an Arduino can be used to emulate the logic chips, and also how we can add a chip to an Arduino to build a project. And in this case, it's an intruder alarm that adds one basic logic chip to the Arduino to enhance its capabilities. So as usual, we have a lot to get going on, so let's start by learning about basic logic chips. The basic logic gates are the fundamental building blocks of all digital circuits. A basic gate is defined as a device that has one output and one or more inputs. We use something called a truth table to define the gate logic. A truth table is a chart that shows all the possible states of the inputs and the resulting output. Basic logic gates use the rules of Boolean algebra for their operation. There are 7 basic logic gates that we will examine today. 3 of them are the most fundamental of all the gates. Today we'll look at 7 basic logic gates, starting with the 3 most fundamental gates. We'll begin by looking at the NOT gate, the OR gate, and the AND gate. The NOT gate is the simplest of all the basic logic gates. This gate is sometimes referred to as an inverter, and for good reason, because the output is the inverse of the input. If you look at the formula that is written below the symbol of the logic gate, you will see that the output Y is the inverse of input A. The overscored line on the letter A indicates that it is inverted. Now beside this we have the truth table, and you will see that for the input A we have two possible conditions, a 0 or a 1. The output Y will be the opposite in both these cases. Now the next basic gate we will examine is the OR gate. Now if you look at the formula for the OR gate, it looks like it says Y equals A plus B, but the plus symbol is actually used as an OR in Boolean algebra. Now to define an OR, the easiest way is to look at the truth table. If you look at the truth table and look at the inputs for A and B, you will see that the output Y is set to 1 as long as either A or B is set to 1. It is also set to 1 if A and B are set to 1. The only condition in which the output Y is a 0 is if A and B are both values of 0. The AND gate is the third fundamental gate, and you will see its formula below its symbol. The truth table for the AND gate shows you that the output Y is set to 1 only if A and B are set to 1. Any other condition will result in an output of 0. The four other basic logic gates are the NAND gate, the NOR gate, the exclusive OR gate, and the exclusive NOR gate. A NAND gate is simply an AND gate with an inverted output, and you can see that from the formula below the symbol. If you look at the truth table, you will see that the output Y is set to 1 in every condition except when A and B are equal. In a similar fashion, a NOR gate is just an OR gate with an inverter on the output. From the truth table, you can see the output will only be set to 1 on one condition, when A and B are equal to 0. Any other condition will result in an output of 0. The exclusive OR gate's formula is shown below its symbol, and you can see the operation of it best by looking at the truth table. The exclusive OR gate has an output of 1 if A is equal to 1 but B is equal to 0, or A is equal to 0 and B is equal to 1. In other words, if the two inputs are different, the output is set to 1. When the inputs are the same, the output is set to 0. And finally, the exclusive NOR gate is an exclusive OR gate with an inverted output. In this case, the output will be set to 1 if the two inputs are set to the same value. If the two inputs differ, the output will be set to 0. You can combine basic logic gates to create other basic logic gates. A simple example is combining an AND gate and a NOT gate in order to create a NAND gate. In a similar fashion, you can tie both inputs of a NAND gate together and use it as an inverter or NOT gate. In fact, the NAND gate is referred to as the universal gate because using combinations of NAND gates, you can create any of the 7 basic gates. A NAND gate combined with a second NAND gate which is wired as an inverter will create an AND gate. This configuration with 3 NAND gates will create an OR gate. And of course, adding an inverted output to that with a 4th NAND gate creates a NOR gate. You can use this technique to create all of the basic gates with NAND gates, and in some cases designers only use NAND gates in their circuits and simply create the other ones themselves. So now let's learn a little bit more about these basic gates. Now, one way to get familiar with logic gates without having to get a solderless breadboard out is to use an online logic gate simulator, and there are a few of them. This one is from a site called Academo, and it's quite a nice little program. You might also want to note that the program itself is open source and is available on GitHub, so if you're familiar with JavaScript and you want to perhaps improve upon it, you can go ahead and fork that on GitHub. Now, this simulator is very simple. As you can see, I've got an input device over here, which is like a toggle switch, and I can click my mouse and toggle it on and off. It's on when it turns yellow. Here's an output device as well. And so what I'm going to do is connect my input to my output device by dragging a line between them. And then when I turn it on and off, the output goes in the same fashion. Now, I can get rid of this line by just right-clicking on it. Now, what I'm going to do is I'm going to add some nodes over here. I'm going to add, let's say, an AND gate over here, and I'll add the node and they give it to me up over here, and I can drag it down and put it, let's say, over here somewhere. And I'll need another input as well because it's a 2-input AND gate, so I'll add another node for an input. It's a little hard to drag the inputs sometimes, I've noticed that. Okay, there we go. I've got my input here, and just turn that off. We'll connect this to the inputs of the AND gate, and the output of that will go to the output. Now, as you can see, both of my inputs are off and the output's off. If I turn one on, there's no effect on the output. If I turn the other one on, there's no effect. But if I turn both of them on, the output goes on. And that, of course, is the function of an AND gate. Now, this can also help you see what can happen when you could connect a couple of gates up. Let's say that we wanted a 3-input AND gate, but only had a couple of 2-input ones. Well, we could combine them and make our 3-input AND gate. Let's add another AND gate. And let's drag it somewhere over here, I guess will be fine. And we will break this connection. Move you over a bit, give me some room to draw. Going to put you up to here. Run you into here, and I'll need another input device as well, because it's a 3-input gate now. Come on, there we go. Okay, let's turn these off. Okay, now what I have is I've got my 3 inputs over here, 2 of them connected to one AND gate, a third one connected to one input of an AND gate, and the output of this gate connected to that as well. And what I'm attempting to do is create a 3-input AND gate. Let's see if it works. If I just turn this on, nothing happens. If I just turn this one on, nothing happens. Nothing happens. These both on, still nothing happens. If all 3 go on, I get an output. And that indeed is the nature of a 3-input AND gate. The output will only be high if all the inputs are high. So as you can see, a logic simulator can be a very neat way of learning a little bit about logic circuits without having to hook a bunch of chips up. So now that we've seen the 7 basic logic gates, we're ready to begin experimenting with them. But before we get started, there is one other consideration that we need to make, and this is more of an electrical consideration. There are some components that are used to glue together, for lack of a better word, all of the logic gates in your circuit. And so I want to take a quick look at those components right now. We're going to look at the buffer, the Schmitt trigger, and the tri-state buffer. These 3 devices can provide the glue to hold your digital logic circuits together. At first glance, the buffer may seem to be the most useless digital logic gate you could imagine. The buffer's output equals the buffer's input, as you can see from both the formula and the truth table. So why on earth would we need such a component? A buffer is there to provide electrical isolation between one section of a digital logic section and another. The buffer can increase the output capability of a digital logic section, allowing you to drive more than one gate. The number of gates the buffer can drive is referred to as its fan-out. The Schmidt trigger I am showing here acts as an inverter, as you can see from both the formula and truth table, but you can get other forms of Schmidt triggers as well. A Schmidt trigger is a device that can clean a data signal. This is actually a form of comparator. In fact, it has two comparators that determines when a signal is below the low threshold or above the high threshold and provide a clean output. Although I've shown a Schmidt trigger here as an inverter, you can also get non-inverting Schmidt triggers, as well as AND gates, OR gates, NAND gates, and NOR gates that have Schmidt triggers built into them. A tri-state buffer is a special form of buffer that has an additional control or enable line. Now, if you look at the truth table, it may seem a little bit odd because you'll notice when the enable line is set to 0, the output Y is set to H instead of 0 or 1. Now, what in the world is H? A tri-state buffer can be enabled or disabled. When the buffer is enabled, it simply acts as a buffer where Y is equal to A. But when it is disabled, it has a high impedance output. That was the H you saw on the truth table. A tri-state buffer is used on data buses where many different devices need to communicate to the same bus, but only one can talk at a given moment. You can also get tri-state buffers that have internal Schmidt triggers. Now here's a digital logic circuit that is currently incomplete. I would like to connect the output of this NAND gate to the 3 unused inputs on the other gates on the right side. Now if I did this directly, the NAND gate may not have the fan-out capability to drive 3 gates. In this case, I can insert a buffer into the circuit and allow it to drive the 3 gates for me without changing the logic. Now here's a circuit that uses 2 tri-state buffers as well as some logic circuitry on the left side. You'll note both the outputs of the tri-state buffers are tied to the input of the buffer that goes to the output. Currently, nothing is going to the output because neither of the tri-state buffers are enabled. If I enable the top buffer, then the logic from the top section, the one with the NAND gate, is passed through the tri-state buffer and through the buffer to the output. The logic below is still ignored. If I enable the other buffer, then the logic from the exclusive NOR gate on the other side will be passed through to the output, and the logic from the NAND gate at the top will be ignored. One needs to ensure that you never simultaneously enable both of the tri-state buffers. Now here's a circuit in which we have a NAND gate driving a buffer, but there is a very long line between the two of them. If I place an oscilloscope at the output of my NAND gate, I can see I get a nice clean digital signal. But if I place my scope at the input of the buffer at the end of the long line, you will see that the signal has been severely degraded. The scope on the output of the buffer shows that the signal that I'm getting out is not the required signal. If, on the other hand, I replace my buffer with a Schmidt trigger, then as you can see, the signal on the output represents the same thing as the signal on the input. The Schmidt trigger is capable of cleaning up the dirty signal. And so now that we've learned about basic gates and the chips that can glue them together, let's start and work with them. So now it's time to take a look at logic families. Now what I mean by families are series of logic chips, all of the basic gates combined in a standard series. And there are a couple of predominant logic families, including 2 very predominant ones. These families are based upon the technology used to create the gates and circuits on their chips. So let's take a quick peek at that right now. Logic families are defined by the different technologies used to construct logic chips. These technologies are based upon the components used and their circuit arrangement. The choice of logic family affects the voltage and current requirements of your circuit. The choice of logic family can also affect the speed and the logic voltage levels used in your design. We can break the logic families down into two sections, those based upon bipolar transistors and those based upon MOSFETs or metal oxide semiconductors. On the bipolar side, a very early form of logic family was diode logic. Resistor-transistor logic replaced diode logic. It had improved speeds and reduced voltage requirements, but unfortunately could not make a NOT or an inverter-type gate. Diode transistor logic, or DTL, replaced RTL and was capable of creating all types of gates. However, DTL consumes a great deal of current. Transistor-transistor logic, or TTL, has become the dominant form of bipolar logic. It can create all of the gates, has very fast speed, and has reduced current requirements as compared to DTL. On the MOS side, we have several technologies that are still very much in use. PMOS, or positive metal oxide semiconductor, NMOS, or negative metal oxide semiconductor, and CMOS, or complementary metal oxide semiconductor circuits. There is also a form of logic family called BiMOS. This is a fusion of both bipolar and MOSFET devices on the same chip. These days we no longer use DL, RTL, and DTL. TTL logic has become the dominant form of bipolar logic. On the MOS side, all of the different logic families are used. However, today in our examples, we will only be talking about CMOS, or complementary metal oxide semiconductors. TTL is a transistor-transistor logic family. This logic family was originally designed using bipolar transistors. TTL logic was invented in 1961 by TRW Industries. The first TTL chips were produced by Sylvania in 1963. The TTL logic family is by far the most popular logic family. There are several variations of these chips. Most of them are based upon 5-volt logic and power supplies. Some newer variations of the TTL logic family use CMOS and BiMOS technologies instead of just bipolar transistors. Here is how you read the part number on a TTL logic chip. The first two characters are the manufacturer's prefix, and this will be unique for every different manufacturer. The next two characters determine whether the logic chip is a military spec chip, in which case they will be a 5-4, or a commercial chip, which is a type 7-4. Most of our designs will use 74 type chips. However, note that military spec chips are sometimes used for designs that need to work outdoors, as they are capable of operating at much lower and much higher temperatures than commercial chips. The next two characters in the part number define the technology used to construct the chip. I'll talk about that more in a few seconds. The next 2 or 3 digits are the part number of the chip in the TTL logic family catalog. Note that some chips also have 2 digits that precede this that indicate the gate count, although this is not very common. Finally, the last letter in the part number determines the type of package the chip is constructed in. Now here's a chart that describes some of the chips in the 7400 TTL logic series and some of the different technologies used to construct them. This is only a subset of the complete list. The 7400 chips at the very top are no longer used. They were the original ones. Now the part numbers remain the same regardless of which series you use. So for example, if you have a 7402 gate, then the pinout of that will be the same as a 74 ALS02 or a 74 HC02. Now many of these use standard TTL or bipolar technology and have a voltage requirement of about 5 volts. However, you'll notice there are a couple of CMOS designs as well that can use different supply voltages. These days, the most common chips you will see are the 74LS series and the 74HC series. If you are doing a new design, the 74HC series is recommended as it can accommodate different supply voltages. Another good series for new designs is the 74HCT series, which will maintain compatibility with the older TTL chips, but offer the advantages of reduced current consumption that CMOS offers. Standard TTL gates have what is referred to as a totem pole output. This uses two transistors which are turned on or off alternatively to send either a 0 or 1 to the output. This design provides low power consumption, and it is also very fast at switching. The same design can be used for tri-state logic chips. In this case, both of the transistors are turned off to put the chip into a high impedance state. Some TTL chips use open collector outputs. In this case, the load needs to be connected between the output and the VCC, which is generally 5 volts. This design allows for a high current output, letting you drive items like LEDs, for example. When using an open collector output chip with other logic chips, you'll require a pull-up resistor. A disadvantage of the open collector output is that it is slower than the totem pole design. Now here's the pinouts for a typical TTL logic chip. In this case, it's a 7400 quad 2-input NAND gate. It's called a quad because there are 4 NAND gates in the package. Notice that this will be the same pinout used for the 74LS00 and 74HC00 and all of the other 7400 series. Note also that the VCC, which in most cases is 5 volts, is applied to pin 14 and the ground is applied to pin 7. These two pins are diagonal to each other, and you'll see this pattern with most, but not all 7400 chips. This makes it very easy when you have them on a circuit board to find the power and the ground. Another popular series of logic chips are the 4000 series, which were developed by RCA in 1968. These chips use a CMOS design for low power consumption. They can operate on a wide range of supply voltages. The CMOS design provides an increased fan-out capability over the TTL design, so less buffers are required and you can connect more chips together. The high impedance inputs used in this design make interfacing much easier. The 4000 series chips, however, are slower than the 7400 series TTL chips, so they're not suitable for all applications. Despite their age, these chips are still very common in new designs. So now that you know more about logic families, let's go and start working with some of these chips. Alright, well, enough theory. Now it's time to actually wire up a few of these logic chips. And I'm going to be using the 74LS series of TTL chips because they're probably the most popular and most easily obtained chips that there are. Now, I'm also going to be taking advantage of the fact that several of these chips have compatible pinouts. Not only do they have power and ground on the same pin, but they contain logic gates that have their inputs and outputs tied to the same pins as well. We're going to use that to check a number of different gates with the same circuit, and then I'll show you another circuit as well that demonstrates 3-state logic. So let's get going on that. The 4 TTL logic chips that I'll be working with today are all packaged in a 14-pin DIP or dual inline package. All of these chips, like most 14-pin TTL chips, have their power or VCC on pin 14 and ground on pin 7. These chips are all quad gates with 2 inputs and 1 output. The first gate has its input A on pin 1. Input B will be on pin 2, and the output or Y connection will be on pin 3. This pattern is repeated for the other 3 logic gates. The 74LS00 is a quad NAND gate. You'll notice that gate 1 has input A on pin 1, input B on pin 2, and output Y on pin 3. The 74LS08 is a quad AND gate with the same pinouts. The 74LS32 is a quad OR gate, and the 74LS86 is a quad exclusive OR gate, again with the same pinouts. We can test all of these chips with the following circuit. You can just substitute whatever chip you want for the 14-pin DIP that is shown here. On inputs A and B, which are on pins 1 and 2, we've arranged a push button with a 2.2K pull-down resistor. This way, when the button is pressed, it'll send 5 volts to these pins, so a pressing of the button will create a 1, and releasing the button will pull it down to 0. I've got the output on pin 3 going through a 330 ohm resistor to an LED. Notice that I'm driving the LED directly from the chip, and this is fine as long as you are only driving one LED. You cannot drive LEDs from all 4 outputs at the same time, as this would likely exceed the maximum current capabilities of the chip. For that application, you would use open collector outputs. This is a very simple circuit to wire up on a solderless breadboard, so let's do that and check our logic chips. Now here's our little digital demonstrator circuit that we're going to use with 4 different chips, and I've got one plugged into it already, and you can see an LED glowing indicating that the chip's output is high. Now the 2 push buttons for the input are buried down here. I'm not sure how well you can see that on the video, and the chip that I've got in here is a 74LS00, and that is a quad 2 input NAND gate. And so a NAND gate's output will be high unless both of the inputs are high. So right now both of the inputs are low because I haven't pressed any of the buttons, and the output is indeed high. If I press one of the buttons to bring an input high, it doesn't have any effect. And the other button to bring an input high also has no effect, but pressing them both simultaneously sends the output low, and that is indeed the function of a NAND gate. It is the inverse of an AND gate. And so I'm going to remove the power and remove that chip and replace it with another one that has a compatible pinout. And what I'm going to put in here now is a 74LS08. And a 74LS08 has the same pinouts, but this is a quad 2 input AND gate. So when I apply power, I have no output because the output currently is low because both of my inputs are low. And if I press one of the inputs high, it's no effect. The other input, no effect. Both of the inputs, however, light the output and send it high because an AND gate is only high on the output if both of the inputs are high. Okay, let's swap that over. And by the way, I'm wearing my anti-static strap, but TTL chips are pretty rugged, and you don't have to observe as strict static requirements as you do with other chips. Now this is a 74LS32, and what a 74LS32 is a quad OR gate. And so we'll hook it back up, and right now I have no output over here, and both of my inputs are at 0. But if I press one of the inputs and send it high, the output goes high. If I press the other input high, the output goes high, and both of them also send it high. And that, of course, is the nature of an OR gate. If one or the other or both of the inputs are high, the output goes high. And now let's place another and final chip in here. And this is a 74LS86. And the 74LS86 is a quad exclusive OR gate. And so I've applied power again, and I have no output. The output is low, and both of the inputs are low. That's what you'd expect. And if I press one of the inputs and send it high, the output goes high. If I press the other input and send it high, the output also goes high. But if I press them both at the same time and send them high, the output is low because an exclusive OR gate only goes high when one or the other, but not both inputs are set high. And so there you go. You can easily demonstrate the operation of several popular digital logic chips thanks to the fact that they happen to have the same pinouts. Now for this next demonstration, I want to show you the operation of three-state logic. Now you recall that we talked about three-state logic. This is a type of logic which, in addition to having an output that can either be high or low, can also have a high impedance output. And this can be used when you want to join two logic circuits together onto a common bus. Now as you can see, I've got a demonstrator here with a lot of wires on it, so rather than showing you the individual hookup, I will explain instead what I have over here and show you in more of a block diagram form of how this is actually working. Now, if you look over here, you'll see I have a couple of sets of dip switches, two 4-position dip switches, and over here I have some LEDs, 4 LEDs. I also have a switch over here that you may or may not be able to see. It's wired to the board, and this is a single pole double throw switch with one side connected to ground, one side connected to 5 volts, and so that way by throwing this switch the output will either go to ground or 5 volts. Now, what this is demonstrating, as I said, is three-state logic. So the heart of this are these two chips over here, and these are 74 LS125s. And what 74 LS125s are they are quad buffer chips. They have 4 buffers in them, but these are three-state buffers, so each buffer has an enable line on them. And so what I've done is I've taken the output of these switches over here. These switches use pull-down resistors so that when they're switched on, they're high. When they're switched off, they're low. And they are being fed into the 4 different gates in a 74 LS125. That's why I have 2 of these chips. There's one for each one of these dip switches here. Now, the enable lines for the 74 LS125s are all tied in common on each chip. So all of the 74 LS125 enables on this chip are in common, and all of the ones in this chip are in common as well. Now, those enable lines are being sent back over here. Now, this circuit uses my switch that switches between ground and 5 volts and feeds that into the input of an inverter. This is 74 LS04. The output of that inverter is fed into the enable line of one of these ICs over here. Now, these enable lines activate the buffers when they go low. They're an active low enable. So if this is set to high, it goes to the inverter, becomes low, and enables that particular set of buffers in that chip. Then it goes through another inverter to go to the other chip. So when this one's enable line is low, this one will be high, and vice versa. So by flipping the switch, I can change the enable lines. And the outputs of these are being sent to another chip, and this is a 74 LS07, and that's just a quad buffer chip, but this chip also has an open collector output, and so I can use it to drive LEDs. So that's basically what's happening. Is I've got 2 banks of dip switches, each feeding their own set of quad buffers, and since the buffers are three-state buffers, I can enable or disable the buffers, and the output of the dip switch that is selected was going to appear on these LEDs. So right now the switch is in this position over here, and I appear to have the output of this particular dip switch over here. So if I change some values on it, we'll see those values changing up on the LEDs over here. Now if I flip the switch over here, I'm now using the values from this dip switch because the 3-state gates are enabled for this switch but not for the other one. And there you go, a fairly simple demonstration of how 3-state logic works. Now for our next experiment, we're going to bring an Arduino into the picture. You know we couldn't go this long without bringing an Arduino in, right? And what we're going to do with the Arduino is we're going to emulate 6 of the 7 basic logic gates. The only one we won't emulate will be the NOT gate, because that's a pretty simple one. What goes in is the opposite of what goes out. This is going to be used to build sort of a little logic gate trainer that shows you the operation of the gates. But you can also use this as an exercise in programming, because this will show you what statements we can use in our programs that are the equivalent of all of the basic logic gates. So let's go and take a look at the hookup for that and for the code of our logic emulator. For our logic emulator, you will require an Arduino Uno, a couple of push-button switches, 2 LEDs to represent the inputs. You can use any color you like. I use 2 red LEDs. You'll need 6 LEDs to represent the outputs. I used green LEDs, but I'm showing yellow ones here as it's easier to see on the blue background. You can use any color you like, or you can even use different colors for each LED. You'll need 2 2.K drop-down resistors for the push buttons. You'll also need 8 220 ohm dropping resistors for the LED. Now any value from 150 to 470 ohms will work. We'll start by connecting the exclusive NOR LED anode to pin 6 of the Arduino through one of the 220 ohm dropping resistors. We'll make the same connection for the exclusive OR LED to pin 7 of the Arduino through its dropping resistor. The NOR LED will connect to pin 8 of the Arduino through a dropping resistor. The OR LED anode will connect to pin 9 of the Arduino through its dropping resistor. The NAND LED anode connects to pin 10 of the Arduino through a dropping resistor. And finally, the AND LED anode connects to pin 11 of the Arduino through a 220 ohm dropping resistor. The A LED anode also goes through a 220 ohm dropping resistor and connects to pin 12 of the Arduino. And the B LED connects through to pin 13 with its dropping resistor. All of the cathodes of the LEDs are connected to the Arduino's ground. We'll connect one side of each of the push buttons to the positive 5 volts from the Arduino. The other side of each of the push buttons will go to ground through a 2.2K dropping resistor. We'll take that same connection on the A push button and connect it to Arduino pin 4. And finally, we'll connect the dropping resistor side of the B push button to Arduino pin 5. And this completes the wiring of our logic emulator. Now here's a sketch that we're going to be using for our logic emulator, and it's a very basic sketch. We start off by defining a number of booleans as being inputs and outputs, because of course we're going to be working with boolean logic, and then we define the devices like the push buttons and the LEDs that we're using to represent the different logical outputs, as well as the LEDs that we're using to represent the logical inputs. We go into this setup. We're going to set up the serial monitor because we're going to display our results there as well as on the LEDs. We'll define our 2 push buttons as inputs, and we'll define all of our LEDs as outputs. So it's all very basic up to there. We go into the loop and we're going to read the buttons and assign values to them. So in A and in B will be the values of push buttons A and B respectively. And remember, when these are pushed, they're going to go to a 1. And then we will write those values to their respective LEDs over here, and then we go and compute the logic outputs. And this is really this part of the code that you're going to want to look at, because it'll show you the symbols that you can use for all the different Boolean operations. Let's go at the bottom after here, and out AND is the AND output, so it's in A and in B. So this is the symbol we use for an AND. Now the out NAND is the inverse of that. So we do in A and in B. And then we use this, the exclamation mark, to invert everything. Now this is the symbol that we use for an OR. And this, of course, will be what we use for a NOR. We'll just invert the OR statement over here. And this symbol is used for exclusive ORs. And so an exclusive NOR is going to be the same thing up over here with an inversion on the front. So there you have an AND, an OR, an exclusive OR, and an inversion, the four basic logic functions represented in Arduino code. Now we'll just go and display the results up to the serial monitor, and then we will write to the respective LEDs to show whether the output is high or low. We'll apply a short delay and run the loop over again. So it's a very simple sketch. Let's go and take a look at it in action now. And so here's my logic emulator, and as you can see, I've labeled all of my LEDs. So these are my 6 outputs, and these are my 2 inputs, the A and the B. And you'll also notice that the serial monitor is displaying the values of the LED outputs as well. Now, right now, it is set with A and B equal to 0, and you'll see that some of my outputs are high, as indicated by the illuminated LED, and some are low. And let's check the logic on that, because it is correct. This is an AND gate, and with 2 inputs low, its output should be low. Indeed it is. A NAND gate is the inverse of an AND gate, so its output is high. An OR gate is also low on the output when both inputs are low. A NOR gate is its inverse, so it has got a high output. And an exclusive OR gate is also low if both of the inputs are low, and so an exclusive NOR gate has a high output. So let's press one of the switches. My switches are buried back over here. And I'll press down the A switch. And as you can see, we've had a couple of changes over here. The OR gate has now gone high because one of the inputs has gone high, and that is correct logic. The AND gate is still low because only one of the inputs is high at the moment. The exclusive OR gate has gone high because one of the inputs is high, but the other one isn't. And of course, the other gates are just the inverse of these gates. Now we'll hit the B switch, and we'll notice pretty well the identical thing, that the OR gate and the exclusive OR gate are now high and the AND gate is low. And if we hit both of the switches and bring them both high, the AND gate has gone high, as you would expect. The OR gate is also high. The exclusive OR gate is low, and that's correct, because the exclusive OR gate will only be high if only A or only B is high, but if they're both high, the output is low. And of course, these other gates are just the inverse of that. And so there you have it, the logic emulator. Now, one thing this would be good for would be for training purposes, and an interesting exercise would be to build this and to not label these and just have someone cycle through the 4 different possibilities of A and B and try to determine which gate is which, and that will show you if you really have a proper understanding of how these logic gates work. So it actually probably does have a practical purpose. Now for our final project today, we're going to combine an Arduino and a basic logic gate in order to create a rudimentary intruder alarm. And this is a circuit that you can expand on in order to create a real practical intruder alarm. Now, as it is, this is just a breadboard experiment, and you can't run the sensor wires very far. But if you were to use this in a practical application, you'd probably want to add relays or opto-isolators onto it. But the way our alarm is going to work is it's going to have 2 connections, or 2 what I call loops, an open loop and a closed loop. On a closed loop circuit, you have a wire that is connected one end and the other, and if this wire is broken in any way, the alarm will go off. And you can use that with sensors such as the foil tape that you place onto windows that would be broken if the window is smashed, or something like a magnetic reed switch that you can place into a door or a window frame that would open when the door or window is opened. And a closed loop circuit is actually the most secure, because anybody trying to thwart the alarm by cutting the wire is actually going to set the alarm off. There's also the open loop, in which you need to apply voltage to make the alarm work, and this is good for sensors such as doormat switches, or for things such as emergency push buttons, so you can have an emergency switch for your alarm. Our alarm is going to have both, and both of these are going to trigger interrupts on the Arduino. Now, the Arduino Uno Arduino only has 2 interrupt inputs, but we're going to be using 4 inputs, 2 closed loop and 2 open loop ones, and we'll be using a TTL logic chip in order to combine all those signals and send them to our interrupts. So let's go and take a look at the hookup of our alarm, and then I'll show you the code, and then we'll demonstrate it. Our intruder alarm is going to be based upon an Arduino and a 74LS132, which is a quad NAND gate with Schmitt triggers. Now, if you don't have a 74LS132, you could use a 74LS00, which is a quad NAND gate with the same pinouts. You would not get the benefit of the Schmitt trigger then. Now, for our alarm, we are going to have a condition where we are going to be looking for an interrupt going high. So therefore, in normal operation, the interrupt should be held low. For the open loop circuit, the circuit that needs to activate an alarm when it goes to 5 volts, we can satisfy this requirement with an OR gate. We'll use 3 of the NAND gates in order to create an OR gate to do that. On the closed loop side, we need a NAND gate because in the closed loop, the inputs will always be held at 5 volts. If one of them goes down to 0, the alarm will be activated. And a NAND gate fits this requirement because its output will be low as long as both inputs are high. But if one of those inputs goes low, it will be high. Remember, a high input to the interrupt pin activates the alarm. Now let's take a look at the circuit we'll use with the 74LS132. In addition to the 74LS132, you're going to need an Arduino Uno, an LED that we will use for the alarm output, a 220 ohm dropping resistor for that LED. Actually, any value from 150 to 470 ohms would work fine. You'll need 2 push buttons for reset and emergency, a 10K pull-down resistor for the Arduino, and 4 2.2K pull-down resistors for the TTL gate. The alarm will also have 3 sets of input connections. It'll have 2 closed loop inputs and 1 open loop input. We'll begin our hookup by connecting the 5 volts from the Arduino to pin 14 of the 74LS132. The ground from the Arduino will be connected to pin 7 of the 74LS132. The LED anode goes to pin 13 of the Arduino through its 220 ohm dropping resistor. The LED cathode is connected to ground. Arduino pin 12 is connected to one side of the alarm reset switch. From that same connection, we will go to ground through a 10K drop-down resistor. The other side of the alarm reset switch is connected to 5 volts. One side of our emergency switch is connected to 5 volts. The other side of the emergency switch is connected to pins 9 and 10 of the 74LS132. That same side of the switch is connected to ground through a 2.2K drop-down resistor. Pins 12 and 13 of the 74LS132 are connected to the OL1 input, that's the open loop input. Pin 1 of the 74LS132 is connected to the CL2 input. Pin 2 of the chip is connected to the CL1 input. All of the alarm inputs are grounded through a 2.2K drop-down resistor. And the other side of all the inputs is a connection to the 5 volt line. On the 74LS132, we'll need to connect pins 11 and 5 together, and we'll also need to connect pins 8 and 4 together. Connect the gate output on pin 6 to the interrupt 0 interrupt on the Arduino, which is pin 2. The gate output on pin 4 is connected to interrupt 1, which is Arduino pin 3. Now you'll need to close both the CL1 and CL2 connections. Breaking these connections will activate the alarm. The OL1 connections must remain open. Connecting these pins together will also activate the alarm. So now that we've wired our alarm, let's go and take a look at the code we'll use in order to make it work. Now here's the code that we're going to be using for our intruder alarm. Now we start off by defining an integer that represents the alarm state, and our alarm can have three different states. A state of 0 means there is no alarm. A state of 1 or 2 means there's an open loop or a closed loop alarm. Now you'll notice we made this integer volatile, and the reason is that alarm state is manipulated in our interrupt handlers, and we need to let our compiler know that by telling it that this is a volatile integer. Now the next integer that we define is the button state, and this represents the state of the reset button that we have connected to the Arduino to reset our alarm. Remember, our emergency button is not connected to the Arduino directly, but it's part of our logic circuitry. Then we have some values for the alarm loop pins, the open loop and the closed loop respectively, that are connected to our interrupt pins. Then we define where we have our devices connected, our alarm LED on pin 13, our alarm reset on pin 12, and the open loop connection on pin 2, and the closed loop connection on pin 3. And pin 2 is also interrupt 0, pin 3 is interrupt number 1. Now in the setup, we're going to initialize the serial port because we're going to also print our alarm status to the serial port. We'll define our inputs and outputs, so the LED is an output and the reset switch is an input. And then we attach our interrupt handlers. Our interrupt handler for interrupt 0 on pin 2 is going to go to this interrupt service routine, and on interrupt number 1, which goes to pin number 3, we will get this interrupt service routine. And these are going to be called on a change of values on the interrupt pin. Now here's the two interrupt service routines themselves. So the open loop intrusion detected is going to set the alarm state the value of 1 and turn the alarm LED on. And it's almost the same thing when the closed loop intrusion is detected, except it changes the alarm state to a 2. So these are the two interrupt handlers that we have over here. We also have another function called clear alarm, and that clears the alarm LED, turns it off, and resets the state down to 0, and also prints to the serial monitor that the alarm has been reset. Note that we don't print to the serial monitor in our interrupt handlers because we can't really use the serial port within an interrupt handler routine. Now we go into the loop, and in the loop we start off by looking at the value of the alarm status. Remember, the alarm state is going to be changed by the interrupt handlers, and so if it is a 0, everything is okay. We just print OK out to our serial monitor. If it is at number 1, though, then we print that we have an open loop alarm condition. And if it's number 2, we print that we have a closed loop alarm condition. The other thing we need to check to see is, do we have a reset push button being pressed? So we measure the button state. We assign button state value, to a digital read of the alarm reset. And if the button state is low, then the button has been pressed. And so we first of all have to see, is this a legitimate reset? Because if the alarm condition still exists, we don't want to reset. So we'll take the value of both the open loop and the closed loop. Now these, under normal circumstances, will be low, but we check them. If the value is high for open loop, then we print that we cannot reset because there's still an open loop alarm. And we do the same thing with the closed loop value. If it's high, we cannot reset. There's a closed loop alarm and we exit. But if none of these conditions are true, then we can indeed do a reset, and we call that clear alarm function that we just saw in order to reset everything. At the end of the loop, we add a slight time delay and do it all over again. And remember that the alarm LED is being driven in the interrupt handlers, not in the loop. It's only being reset when we call the clear alarm function over here. And so this is the code for our intruder alarm. Let's go demonstrate it now. So here's my alarm circuit on a solderless breadboard. Also, you can see the serial monitor display, which is displaying okay right now because we're not in an alarm condition. Now I'll point out what some of the components are here. The LED is my output LED, so that'll be illuminated if we're in an alarm condition. The red push button switch over here is my reset switch. That's the one that's connected directly to the Arduino. Buried back in here, I'm not sure how well you can see it, is a black push button switch, and that's connected to the logic chip, and that will trigger an open loop alarm. So if that is triggered, it'll close that open loop and cause an alarm. It's an emergency push button, so to speak. And these long orange wires here are my closed loop alarm. They're connected to 5 volts, and if one of them becomes disconnected or broken, then the alarm should go off. So right now, let's try my emergency push button. I'll hit the push button. And as you can see, I'm displaying open loop alarm, and my alarm is illuminated. And I can hit my reset switch, and it says alarm reset, and the alarm is back and armed and okay. So now let's break the closed loop. I'll just pull one of these orange wires here. And again, I've got a closed loop alarm. The alarm's illuminated. Let's try to reset this right now. If I do, it can't reset. It says closed loop alarm condition still exists. And so I will put this back to 5 volts over here. Note the alarm is still on until I go and reset, and that turns it off. And so that's the function of our basic alarm with an Arduino and a TTL logic chip. One interesting story of the days of early digital electronics is the story of Gordon Moore. Gordon Moore was a very accomplished gentleman. He was both the co-founder of Fairchild Semiconductor and of Intel, and he was also CEO of Intel. And in 1965, he was showing off Intel's latest accomplishment, which was to put 60 transistors onto one silicon chip, a great achievement in 1965. And Mr. Moore predicted that every 2 years, the number of transistors that they could put onto a chip would double while the cost would be halved. Now, this prediction seems to have pretty well held up since then. Mr. Moore's own company in 1974 released the world's first commercial microprocessor, the Intel 4004, and that chip had 2,600 transistors on it. Fast forward to today, and we have a lot of transistors, which are all MOSFETs, on our chips now. AMD has a microprocessor that has a whopping 38.54 billion MOSFETs on it. NVIDIA has a graphics processor that has 58 billion MOSFETs on it, but even these numbers are nothing when we compare them to memory chips. Now, Samsung has developed a technology with their VNAND chips of using one MOSFET to store 4 bits of data, which means you need 2 MOSFETs per byte. And they have a 1 terabyte memory chip, meaning that that chip has over 2 trillion MOSFETs on it. One little trivia thing is that if you take a look at all the MOSFETs that we've placed on all of the silicon chips throughout time, it makes the MOSFET the most manufactured device on Earth. And with saying that, I would like to thank you for taking all of the MOSFETs in your device and aiming them at YouTube so that you can watch this video. I really appreciate it. If you'd like to see more videos from me, the best way to find out about them is to subscribe to the YouTube channel, and you can do that by clicking the subscribe button just below this video. And after you do that, also remember to click the little bell notification, and that way you'll be notified every time I make a new video. If you want some more information about the stuff we talked about today, about digital logic, you can go to the dronebotworkshop.com website and you will find an article that accompanies this video. There's a link to that article in the description of the video. While you're on the website, please consider signing up for the newsletter. It's my way of staying in touch with you and letting you know what is going on in the workshop. And of course, if you want to discuss electronics, be it basic digital electronics or very advanced microcontrollers, the best place to go is the DroneBot Workshop forums, and there's information about joining the forum right below this video as well. So until we meet the next time, please take care of yourself, please stay safe in these trying times, and I will see you again very soon here in the workshop. Goodbye for now.